Okay, so here's an example of missing at random situation. Okay, I just thought about it now, so maybe it's incorrect, but here is an example. So let's say you're getting data from about let's say income level, okay, and you have observed one of the features, observed features is male or female, okay, and you're only getting data, okay, you're only observing you're only asking for income level if they are, let's say, females, okay. Then in that income column you'll have missing data for males and some numbers for females, let's say. Now your missing data is not a function of you missed the data not because of something you did not observe, I mean not because of the intrinsic value of their income, for example. You missed that entry, the income level, because it only because of the observed data, which is the male female column. So male female column is observed, but the income level was not observed, condition on you being male or female. That's an example of missing at random, okay. Is that example clear? No?
But yeah, it doesn't seem random.
It's yeah, that's true. Oh yeah, it's deterministic. Yeah, it's a corner case. Yes. So the Rij, so the R, yeah, the mask is like all zeros for females and then all ones for males. So that's an extreme case, like. But you can say, it's fine. It does still fit into that example. Yeah, it doesn't look like random. That I agree. Any other questions? Okay, so for the next, I guess, 45 minutes or so, what we're going to do is try to do three things. Okay, three things. First is, I'll just write down the template for what is a generic forward stage-wise additive modeling procedure. Okay. Second thing I'll do is Adaboost is essentially belongs to the FSAM family, and why does it work? We just saw a procedure that you start with some data, upweigh downweigh the data points and have this weak classifiers, you concatenate them, add them together. Why does it work? Why does it do good predictions, right? So in fact in the notes you'll see that they're comparing decision trees with Adaboost, and they show that Adaboost achieves like really high accuracy or very low test error as you keep boosting, as you keep adding these weak models. Okay, in that example they were adding just what are called decision stumps, okay, which are just two leaf node trees, which means that you have an input feature, just break it into two regions, and that's it. So you only have two regions and that's it. So you keep breaking it into so these are really weak classifiers, because you're, first of all, if you have p-dimensional data, you're only picking one feature and then breaking it into two. How well would that predict your class, right? It may not predict really well. So that's what. So we'll try to understand why does it work. Okay, there's only a partial satisfactory explanation for this, at least from me. You guys can look it up. There's some interesting work, I think, in the 2000 to 2010 decade about why does Adaboost work. Okay, and the third thing is we're going to look at another family, which is another gradient boosted decision trees, which also belong to this forward stage wise additive models. And the key part there would be the gradients. Okay, so we'll try to understand from the gradient perspective. Like really, we saw gradients before when we said, okay, we can solve linear regression models we can get them using gradients and gradient updates. So we'll revisit that idea here. Okay. Any questions about what we're going to do next? No questions? Okay. So forward stage-wise additive models, what is it? It's basically the following. Okay. First step, initialize. Actually, the indexing is 0, but let's say f of f1 of x is 0. Okay, it's a predicting always 0. So I'm writing it in terms of a generic supervised learning problems. It could be regression or classification. So Adaboost is for classification, binary classification actually, the version that I wrote previously. So let's do this. So first you start with some function that's a 0 or something constant, and then you have for loop for m is equal to 1 to, let's say, capital M, let's say, or 100. You do two things. First one, you find a parameter. I'm gonna say theta m, which is the arg min of some, I guess, search. You are searching over parameters of the mth model, and the best parameters, let's call it theta m. So arg min over my data I is equal to 1 to n of some loss function, where what is the loss function doing? It's comparing two things, the ground truth and the predictions, right? That's what a loss function does. So the ground truth is, let's say, yi, and the prediction is going to be sum of f oops, one second. F of m minus 1 of xi plus some new model, let's call it b of theta. Oh, sorry. B of xi with parameter theta. Okay. So I wrote it a little bit carefully. I'm just saying that you want to find. So you've already figured out. You're in the mth step. You're trying to add the mth model. Okay. In the mth stage, you're adding the mth model additively. You're creating an additive model. So you look at it's fine. So you look at, okay, let me put the b part. So what is fm of x is going to be fm minus 1 of x plus b of x with theta m. So all I'm saying is you keep a running average of your models. Okay, so the running average of the previous m minus 1 models is fm minus 1. Okay, so it's like an addition of all the predictions of the previous m minus 1 models. That's fm minus 1. Okay, it's getting updated once I figured out the next, the mth stage best model. If I figured out, that's this guy, I add it to fm minus 1 and I get fm. So fm is like a aggregation or average of all these, not really average, it's the sum of all these stage wise models. Okay, so this part is clear. Updating a bunch of additive models, additive as in like this update is clear. I created a new model, I just added to my previous collection of models, previous sum of models, right? This part is saying you're making a prediction for the ith observation using the previous m minus 1 models. Okay, I want to figure out, you're making a prediction, it could be off. I want to figure out another model, which is the b, right? B at this data point along with your previous models can predict the yi better. Okay, that's the b I want, and b for that I'll figure out the theta. So I'm trying to figure out the theta such that I'm able to predict, somehow like the residual for this ith observation. For the ith observation, let's say I'm already predicting, let's say the yi is 10 value, okay, some value. Previous all models give me a prediction of 8. Okay, then I have to somehow compensate, otherwise my loss is going to be, let's say loss is least, square loss, then my loss is going to be 2 square or something, right? So somehow the B, I need to change the parameters of B such that B predicts 2 here, so that I can kind of kill the get the loss lower for this observation. But then it's not just for this observation. The parameter is shared across multiple observations, so you can't just randomly kill the residual for this observation. Okay, so that's it. So that's forward stages additive modeling. And the way I wrote this, there's really no data manipulation. There's no weights, right? So there's no data change that I was doing with Adaboost, right? But at least B part was common, right? B part was just Adaboost was just adding models, and since it was binary, it was only specific for binary classification. We took a sign of this FM function would be either positive or negative, and it would classify, right? So let's in the next 5 minutes, let's try to understand 2 things. One is why is Adaboost a part of forward stages additive model, as well as why does it work. Okay, so why does it work can be easily answered if I can tell you why does forward stage-based additive modeling work, right? If forward stage-based additive modeling works, then Adaboost is I can show you that, okay, Adaboost is the same as this, so therefore it works. Now, why do you think this works? As in, why does it build if I do it for m iterations, okay, 10 iterations, 10 stages, then I'll get a f10 of x, and the question is, why does f10 of x perform well in terms of prediction? And the answer is, so here the performance is actually just with respect to training, right? So there is really, we are kind of ignoring the fact that there could be a discrepancy between test error and training error, but you can see that I start with no model basically, or some constant prediction model, and I'm actually really correcting for residual. So I'm really minimizing with each additive component that I'm adding here, I am actually minimizing my training error, right? The training error for this guy FM has to be lower than the training error for the previous model. If it was not the case, then I could always set B to be 0, so that it is the same, right? So training error I can really drive down to 0, right? But then you can say, oh, okay, you're only talking about training error. Why does it? I said it performs well. It probably is an empirical inference on how maybe test error is low, it generalizes well, but those I'm not saying actually. I'm just saying that it clearly, in terms of training error, it does decrease the training error as you add more models, right? It turns out that empirically, it turns out that it also does. It has issues with overfitting, or sometimes it does well by doing this. Okay, so that's test error. I'm not really saying anything. Yeah.
Did you explain how you add the models, 2 models together? Or is that different for each type of?
It's just a summation, right? So adding 2 models together is this part, is this underlying part here. So I have so we don't really like. So if F was what are the models we have seen so far? We have only seen, let's say F was a decision tree. So let's say B was a decision tree, sorry, and we'll get to this. And then previous m-1 were also decision trees. Then adding these is just for conceptual sake. We're going to retain all of them. Okay, we're not going to really add them. At a given test point, we're going to just evaluate what is my prediction for each of the tree and then add them together. That's it. So because my prediction is going to be the sum of all these Fs.
You're going to get the probabilities for each observation to make a prediction.
So I was talking in terms of regression, but for classification, yeah, you will keep. So Fs will actually predict class propensity, like basically probability of being in class 1, probability of being in class 2, probability of being in class 3. Yeah. So Fs would not be predicting one number, but be predicting 3 proportions. Yeah. And then you would average those proportions. Not average, sorry, sum those proportions. Yeah. I keep using average. It's not averaging here. It's adding. So we are only working on residual. So you're already making some prediction. Something is left. Only I'm trying to make that prediction. Okay. Yeah. So addition. So I explained in terms of trees, and we'll see that again actually now pretty soon. I think the tricky part is this actually. So it's not really tricky. What you do is for each observation you actually make the predictions from before, because you already have fm minus 1. You already have your pre-trained previous models. You get some numbers, and those will be just numbers here, and y's are numbers. So only thing you want to figure out now is this parameters of the b function, which is a new model. Okay, I'm just using b, but you can call it f. I didn't want to overload. Yeah. Is there any other question? Yeah. You can change the model if you want. You can, like the first model could be a linear regression model, second model could be something else. Yeah, it could be a decision tree, third model could be Adaboost if it's classification. I mean, you can do, I mean, I'm not really specifying what model family it belongs to. But here, yeah, I mean, so that's a good question and you should investigate it offline. Yeah. Any other question? So I guess the only thing left is to show that Adaboost is also like it actually belongs to power stage-wise additive modeling class, right? Because we just saw that this modeling class really drives down the training error for sure. So it has no issues with bias as long as the f's are decently good enough, the models that I'm adding. So but I'm only painting a partial picture because ideally you want to say that FSAM, these models are really good in terms of generalization, which I'm not really saying anything here. Okay, I'm only saying that they bring down the training error. So let's see, why is Adaboost in FSAM? Okay, so this is a shorthand for in. Actually, in is also small, but just 2 letters. So Adaboost is actually, I think I told you guys, adaptive and boosting. Adaptive because data weights are changing. Everything else is the same. X's and Y's are the same. Data weights are changing. So that's adaptive. Boosting just means adding models, I guess. Yeah. So for that, we make 2 observations. Okay. Actually, this underlined in is actually approximate. It's not exactly. So that's why I said it's a partial explanation of why Adaboost procedure works. So Adaboost is doing something different, right? It's just reweighing data points and getting a weak classifier, building another weak classifier, reweighing data points, building a weak classifier. Here we didn't say that. Here we said build a model, get the model's predictions, and then build another model. So there is no data reweighing. Okay, but essentially almost the same, approximately the same. Is because of the following. So let's assume that our loss function. So we first of all we are in binary classification, right? Because Adaboost is in binary. Okay, -1 and 1. Okay, so we're going to use a loss function which is L of y comma f of x, which is e to the power minus y times f of x. Okay, this is a loss function. Why? Because it's positive. E to the power something, anything is never going to be less than 0. Okay, and so let's think of it. Let's evaluate. So if y is 1, okay, if y is 1, then my f of x should ideally be the same sign. Same sign as y. Y is 1, so f of x hopefully is positive. As in, yeah, f of x can be positive, or if f of x is like the sign of a bunch of functions, then it's +1. Okay, if they both agree, then it's e to the power minus of 2 positive things. It's a small number. E to the power minus something which is positive is a small number. Okay, like think of y is +1 and f is +1, then e to the power minus 1. Okay, that's a relatively small number. But if y is positive, y is +1 and f is -1, then there is a loss which is e to the power 1. Okay, e to the power 1, because 1 times -1, right? So every time I make a misclassification, I have an error of e to the power 1, and whenever I don't make a misclassification, I have an error of e to the power -1. Okay, simply intuitively speaking. So that's why this is a loss function, it does penalize if you misclassify relative to when you don't misclassify. Okay, there are many loss functions like this. Maybe if I have time, I'll just give an example of a few other loss functions. But so let's say this is a loss function in forward stage-wise additive modeling. Okay, so we'll start from FSAM algorithm and see if it kind of resembles Adaboost type of setting. Okay, Adaboost is details, procedure details. So if this is a loss function, then you can already observe, you can already make an observation, which is that let's say I have an observation yi, and let's say I have my previous models fm minus 1 of xi, and I want to figure out a new model b of xi at a parameter value theta. Okay, so right, I mean, for the ith observation I have three things, right? Yi, which is the target, my previous predictions, prediction that I could make, and what is left, which I want to hopefully optimize for. Now for this, what would be the loss function? It's e to the power minus yi times fm minus 1 of xi plus b of xi at theta, right? I just substituted what was there in the previous slide, and this is actually is the same as e to the power minus yi fm minus 1 of xi times e to the power minus yi b of xi theta, right? I just e to the power a plus b is e to the power a times e to the power b, right? Now this guy is all data, right? I mean, in the sense at this stage, I already know all the previous m-1 models. I already know its prediction. I already know my yi. So this number is, you can think of this as approximating the weight for your ith observation. Okay, and this guy, second term, is the usual loss function. This is the loss function, e to the power minus yi times y times f of x. In this case, f of x is like b of xi comma theta, right? I mean, the parameter is theta, but this is basically minus y times f of x. That's the second term. So this is a loss, the second term is a loss, first term is like the weight, so it's like the weighted loss function. And you're trying to find the beta which minimizes the weighted loss function. Okay, so that's what you were doing in the Adaboost case, right? In the Adaboost case, you had a weighted loss function because you were maintaining weights for the data points. This is like a weight for the data point, considering what all your predictions you could make for this data point, is saying that if they don't agree, then the weight is going to be high, and if the weight is high, then you better do good with the how the new function does on this point. Okay, is this clear? Any questions? I said it's only approximate because there are a few other things. First of all, I didn't tell you how the weights are updated, right? So here the weights are updated because you change from fm minus 1 to fm, but in Adaboost procedure there's slightly different update procedure. So, and there's also no notion of a specific loss function in the Adaboost procedure. Okay, there is no, I didn't say anything about a loss function, just train a model, train f1, train f2. I didn't say whether you use a exponential loss function or not. Okay, so there is some incompatibilities, but there's a partial explanation of what's going on with Adaboost. There are full-fledged papers about this from 10 years ago. Yeah.
If you have multiple labels,
Yeah.
metric system is what?
Adaboost is Adaboost.m1, or the version that we saw today is only for binary classification. Yeah, but the forward stages additive modeling is true for any whether classification or regression.
What was theta again in that formula?
This theta is the parameter for the model. I mean, for the B model. The model B, it has to make a prediction for a given point xi. Hopefully it matches yi, but its parameter, the model's parameter is theta. So think of if it's a tree, then it's the Cj, R, the C and R's regions and the constant values in the regions, for example. Or if it's, let's say it's linear regression, then it's just be betas, the beta coefficients.
curiosity. So if the problem is a multi-class classification,
Yeah.
how do -1 and 1 values change for that? Do we use a different loss function there? Or?
No, so if it's a multi-class classification, you just have to look at this. You can't use Adaboost. So here you can pick y's to be either -1 + 1, -2 + 2, whatever. Let's say 4 classes. You can choose -2 + 2, -1 + 1, or you can choose 1, 0, 1, 2, 3, 4, 0, 1, 2, 3. Sorry, anything is fine. I mean, you get to choose what loss function you want to use. It could be the exponential loss. That is the loss that I wrote in the next slide. This is called the exponential loss function, and there are a few other loss functions. I mean, in SVMs, there's something called hinge loss. Okay, there's something called ramp loss. There's a misclassification loss, which is like the 0, 1 loss. So there are many loss functions, and maybe I'll comment on loss functions again. Actually, maybe right now, I'll just comment on loss functions. So before we get into gradient boosted decision trees, I'll just talk about a few loss function examples. Yeah, for regression, there's, I mean, you can use many different loss functions. So let's say for regression, it's y minus f of x the whole square, or absolute value of y minus f of x. Let's say y is a scalar, or you can have a linear combination of these two. Like okay, maybe not linear combination. Let's say, yeah, you can have this. This is one example. This is one example, or you can also have loss between y and f of x to be equal to this if f of x is small, so less than, if f of x is small, otherwise. So this is called a Huber loss. Okay, and how does it look like? It's basically saying if f of x is small, it's like quadratic, and beyond some point it's linear. Okay, instead of going quadratically up, it just becomes linear here, and it's quadratic here. Okay, that's an example of a loss function. It's used in what is called robust statistics, or basically if you want to have, if you have a data point here, you don't want to penalize the square of that, because then it'll be like completely off. Okay, so somehow it's saying like if points are far away, sorry, not points, but the loss function, if y and f of x differ too much, then I'm only going to penalize them linearly, absolute value difference. If they're too close is fine over here, but in some intermediate region, I'm going to penalize them like quadratically, some expression like that. So that's for regression. For classification, the best way to do this is probably using a diagram. So let's see. Oh man, I shouldn't have done this. Okay, so this is the 0, 1 loss. So what am I plotting on the x-axis? Okay. Oh, in the previous, okay, here also, what am I plotting on the x-axis? On the x-axis, I'm plotting, let's call y minus f of x is z. Let's call this z. So I'm plotting z on the x-axis, and the loss of z on the y-axis. Okay. So it's z square versus absolute value of z, right? So like this loss function only is just like this. Okay, so L of z versus z is like this. It's like a V-shaped thing. If z is not exactly equal to 0, either positive or negative, it's just the same value. Okay, and the quadratic one is something like U-shaped. So classifier, so here again it's a z, okay, but this is equal to y times f of x. Let's say we are doing binary classification. Okay, so this is a 0, 1 loss. Why is the 0 1 loss? If y is positive and f is positive, then z is positive, then I'm saying it's the classes are aligned, no loss. If y is negative, f is negative, again the product is positive, classes are aligned, no loss. Okay, and if it's the opposite, then there's a loss of 1. And exponential loss is basically a loss function which looks like this. Okay, at y times f of x is equal to 0, e to the power 0 is 1. Okay, this is 1 here, this point is 1, and otherwise it's just it's basically dominating this step function like this. Okay, that's exponential loss. And something called hinge loss, I guess. Hinge loss is almost the same, but it's like this L. Okay, so what is this intersection point? Something like 1, let's say. Again, it dominates the 0 1 loss. Okay, they're just examples of loss functions you could define, but let's not worry too much about the choice of loss functions. Everybody's tired? Okay, so let's actually go to the main part, which is gradient boosted decision trees. And it's not difficult. We'll just understand, the only twist is going to be how do we add models. So we already saw the FSAM template here, right? We already saw this. This is what even gradient boosted decision trees also have to do. Okay, but there will be a nice trick in terms of how do we add, how do you get the new model. Okay, so for that, I'm gonna first just tell you what the procedure is, and then I'll kind of reason about it. Okay, so that you know at least the procedure. Okay, so by the name, decision trees are the ones which are going to be optimized in every stage. Okay, decision trees, we're only going to look at decision trees. Boosted decision trees just means we're going to do this forward stage wise additive modeling. Okay, so we're going to add one decision tree in every stage. Now the only mysterious thing is this gradient part. Okay, now okay, and to understand that, so let me tell you what the procedure itself does. So if you already have a so let's say you have a model already. So you already have a model fm minus 1 of x, right? So that's so I'm thinking of only the mth stage. What happens in a gradient boosted decision tree model? Okay, you already have fm minus 1. So what you do is for every data point, so which means that I have xi's and yi's, right? That's my observations, n of them. For every data point, what I'm going to do is find the gradient. Okay, I'm going to call it g of I in the m stage. So I corresponds to the ith observation, m corresponds to the mth stage. I'm going to find the gradient. It's actually just going to be a number, and what is it? It's the gradient of the loss with respect to yi and a variable. Okay, call it z. With respect to z at z is equal to fm minus 1 of xi. Okay, this is it. This is the gradient. So let's understand what's happening. So let's focus only on the ith observation. Okay, I already have the previous m minus 1 model, previous m minus 1 models added together. That's fm minus 1. Okay, that at a given observation point, ith observation point, evaluates your number, right? That's fm minus 1 of xi is some number, right? Now what I want to do is so my loss function takes two inputs, right? So my true value and the predicted value. Okay, all I'm saying is the loss function second argument, I'm going to take a derivative with respect to the second argument. Okay, the second argument is a scalar. If you ignore the model part of it, it's supposed to, y hat is supposed to be some number. So I'm going to ask for the gradient with respect to that number. Okay, at the loss function, think of loss function as squared loss, for example. It's a squared loss function. You can take the derivative with respect to the second argument. Squared loss is symmetric, but it's fine. And you have to define, and it turns out the gradient could be a function of the point where you're evaluating it. Okay, for example, if you have something like a quadratic, the gradient at this point is different from gradient at this point, right? It will depend on where you're evaluating z1 and z2. So that's all I said. So if a gradient depends on the value where you're evaluating it, we're going to evaluate it at what my previous prediction was. Okay.
Is this for a regression you're doing here?
Yeah, right now I'm starting with regression. Yes.
Because otherwise it would be a class rather than a number.
Yes. If you have k numbers, then you do k derivatives. Yeah, separately. Let's say if you have 3 classes, then you'll take the z, instead of z there will be 3 numbers, which hopefully can tell you how good the prediction is, right? Your loss function could be not just misclassification. Even misclassification depends on what are the three numbers in the 3 class classification, right? So all I'm saying is, first of all, the loss function has to be differentiable here. Okay, but modulo that, if you have a classification problem, you will have 3 different these GIM for the first class, GIM for the second class, GIM for the third class. There will be 3 numbers. But for now, let's focus on regression. All I'm saying is, given the previous m-1 models, for the ith observation, I can take the gradient of the loss with respect to the ith observation's second argument and set it at the value at the current model value. Current doesn't like the previous m-1 model's value. Okay, so that evaluates as some number. Okay, that's it. You do this for all the numbers, so all the observations. You will get gi of m, which is going to be scalars for every observation. So then what you do is you have data x, that the thing which I wrote here, and you have y, right? You drop the y and you just concatenate all the g1m all the way to g nm. Okay, so you found a gradient for each observation, right? G was a scalar because the whole z is a scalar, right? I'm saying you found this for each observation, just concatenate them one below the other. You got this vector. You ignore the y and think of this as now your targets. Okay, in fact, actually minus of this as the targets for simplicity. I mean minus or plus, it doesn't matter. Okay, that's it. So you can build a decision tree with these 2. You saw the decision tree building process for regression in the first part of the lecture, right? Build a decision tree for these 2. Okay, and that's it. That's going to be your tree. That's going to be at least so from the decision tree. What you do is there's a little bit of nuance. You take the regions of that tree. The coefficients you slightly change them, but that's second order issue. Okay, let's using the same coefficients. That's fine. And that's it. That's your tree that you add to your model. So fm is going to be fm minus 1 at x. Okay, a model like this plus the tree that I constructed when I regressed x with g when I did this. Okay, the tree will have some parameter. Let's call it theta m at x. Okay, that's it. That's my forward stage wise. Sorry, not forward stage, gradient boosted decision tree. Yeah.
The derivative you're taking there of the loss function.
Yeah.
You have to set that equal to 0 in order to get the values.
No, you don't have to set it equal to 0. I'm not setting the gradient equal to 0 here. I'm getting the gradient value itself. I'm not trying to solve for something here. Okay. See, z was free. I could choose anything. So if think of the loss function. Let's be specific. So yi minus z the whole square. Let's say loss function is squared loss. Okay. This is the function. Right. This is pretty much the function for the ith observation. Forget about everything else. ith observation is this is the function. So I want to find what is the derivative with respect to z. Okay, this is minus 2z, minus 2 yi minus z, right? That's it. But it involves z, so I need to set it to some value. So I'm saying z should be equal to the previous fm minus 1 of xi. Okay, this is some number, this is some number, so this whole thing evaluates to, let's say, 10. Okay, could be 10. That's it. That's my gi of m for the ith observation. Similarly, there will be another gj of m for the jth observation, and so on, like first observation all the way to n observations. I just concatenate them together. That's my, that's a vector of n cross 1. Instead of y, which was n cross 1, I'm going to use that as the targets. That's all. That's the only difference. Okay, so this is gradient boosted decision tree in a nutshell, and now I'm going to tell you why this makes sense. Okay, so the procedure is clear, right? You just build a tree with respect to x and modified y's, and then that tree added to your previous collection of trees is in that stage, and then you keep adding trees again and again, right? You repeat this, the same forward stage as the additive modeling concept. Now, why does this make sense? Is because of the following. Okay, so think of this way, right? So if I had this loss function at yi comma fm minus 1 of xi, okay, in general I'm supposed to add plus b of xi at theta, right? This is what I'm supposed to do. Sum over I is equal to 1 to n and minimize over theta, right? This was the step in that forward stage wise additive modeling template. Okay, let's say I don't want to do this. What if I decouple these corrections, or these basically these b? So even if I figure out the theta, at that theta I find b of xi, so I make my prediction. Okay, there will be some number, right? For each observation there will be some number. That's this part, right? The underlying part. That's some number prediction that I'm making, even if I optimize. So let's call for the ith observation that number to be zi. Okay, whatever that prediction is. Okay, and similarly for each observation, let's call it z1 to zn. Okay, then my loss is actually yi fm minus 1 of xi plus zi. Okay, and now since I use zi z1 to zn, I'm going to say let me minimize over z1 to zn. Okay, it's a little bit of a hand wavy thing, because this is not actually I mean, this is fine as long as I say zi is equal to b of xi comma theta, but I'm not saying that. Okay, okay, so now in the gradient boosted decision tree procedure, I said, I mean, so the z's in that procedure were minus of gradient of the loss with respect to yi comma z divided with respect to z at z is equal to f of minus 1. Yeah, I can put it zi as well. Let's call it zi. Okay, okay, so this term is supposed to be like the same as the prediction of my so this term here is supposed to be the output of my tree model, right? So if I want to add the tree in the nth stage, that tree is going to make a prediction. That prediction is what the zi should be for the ith observation, right? In the GBDT procedure I just mentioned, the target, so this was nothing but minus gi of m, right? So remember, in the in the decision tree procedure that I mentioned 2 slides ago, here I said use G minus GMs as the targets. So I'm saying use this guy as a target basically. Okay, right? I mean this is nothing but minus GM. So all we're saying is if this is a target, then all we're saying is for each observation, we are saying we're going to update fm xi as fm at xi xi fm minus 1 at xi minus the gradient of loss with respect to yi. I mean I can write z, okay, zi respect to gradient of zi given zi is equal to f m minus 1 xi. Okay, right? So if actually let me use some other z here. Okay. Anyway, all I'm saying is we use the targets minus GMs to build a tree, and the tree is going to be added to the fm minus 1 guy anyway in the forward stages additive modeling. So essentially what we're doing is this, right? So we are saying fm minus 1 was there, now minus GM was being predicted by a new tree. So the minus GM is nothing but minus of the gradient of the loss with respect to that argument at z is equal to something, right? So this is nothing but a gradient step, okay, for this observation. So that's I guess the key part of this this gradient boosted decision tree is that we are using the idea that we can take a gradient step at the current function is fm minus 1. I'll take a gradient with respect to that second argument and evaluate it at fm minus 1, and that's going to be telling me how to minimize my loss function. In fact, I'm doing a negative gradient step. Okay, that's going to tell me how to minimize my loss function by taking this negative gradient step. Yeah.
And so this is giving you, like, if this were a decision tree, for example, it's giving you a new decision tree.
Yeah.
And unlike the Adaboost, in the end, you're not going to sum up all these trees. You're just getting a new one, and then you're going to work from that and get a better one, and a better one, and a better one.
Good question. So actually, we are summing up trees. So fm minus 1. Think of I already have m minus 1 stages done. In each stage, I got a tree. Okay, but they are already fixed in the sense I already figured out the regions and the constants, for example, in that tree. So they're all fixed. So at this point, I want to figure out a new tree. Okay, and in terms of procedure, I said to figure out the new tree, find the gradient with respect to, for each observation, find the gradient with respect to its second argument. You'll get some number because you are evaluating at the current fm minus 1, which are all fixed trees. You just add them up, whatever number it is, right? You get the gradients and build a tree with respect to which are predicting those gradients. Basically, the tree is predicting those gradients. Okay, and that's it. So adding the tree is the same as adding a gradient step in your optimization problem. That's the idea. The key idea is you building a tree which predicts the gradients is the same as taking in fact it predicts the negative gradients, and so it's the same as taking a negative gradient step in which is this step here is a negative gradient step. I'm moving from fm minus 1, taking a negative gradient with respect to the second argument of the loss function, so that I can improve I can minimize my loss function. Okay.
And you're sort of discarding f of m minus 1, and you're going to then work from f of m.
Yes.
A new one.
I mean, it's not discarding. So the tree that I created in the mth stage and all the previous m minus 1 trees, I'm going to remember them, and that's my whenever I want to make a new prediction at xi, those m minus 1 previous trees and the mth tree together are fm minus 1. I'm not going to forget them, because if I want to evaluate at xi in the next stage, I need to evaluate. I need to plug in xi at each of these trees and add all the predictions together. Okay, I'm not going to forget the trees, if that's your question. So yeah, so all we are doing here is previous fm minus 1 had m minus 1 trees. Because we are making predictions on the negative gradients, that adding the tree is the same as taking a negative gradient step. Okay, and taking a negative gradient step kind of is the template for minimizing loss functions. Okay, So if you had a loss function with some parameters, you would have theta kth iteration or theta mth iteration is theta m minus 1th iteration minus the negative gradient of the loss with respect to the parameter. Okay, here we are not taking it's slightly nuanced, a little bit nuanced than that, but that's what we are doing. Okay, there's one, so it's a little bit heavy, but yeah, go ahead.
How does it work when m equal to 1? So initially you should consider when
M is equal to 1, so fm minus 1 pick some constant.
so it will become sort of like mean you are taking it from where you are coming up with.
Yeah, you can start with 0. I mean, in the previous thing I said take 0, right? I mean, you can have a constant prediction model. I mean, so just go back to the FSAM template. Whatever I said is fine. You can also take the mean of the output values if you want. Yeah. Wait, what was I going to say? Yeah, there's a little bit more nuance because the tree construction I said, the tree construction regresses or basically builds a regression model which tries to predict the negative gradients. That gets you the regions and the coefficients. But there is a slight update you need to do the coefficients. Okay, that's a second order. When I say second order, it's not like the most important critical thing. First, you understand what's happening. Adding a tree in the mth stage is like essentially the same thing as predicting the negative gradients of the loss function with respect to its second argument. Okay, evaluated at fm minus 1. Okay, so basically you already have fm minus 1. It's performing at some level, and you're saying, okay, I'll take the negative gradient with respect to that in the n-dimensional space in this case, and that's going to give me a better model. Okay, so that's a key part. And the slight update to the trees, once you get the tree, once you do this regression between x and the negative gradients, you have to do a slight update on the coefficients which are scalar numbers in the region. Okay, well, that's an easy problem. Just believe me, and I can discuss it after the break if you want. But this is the key part. But even if you don't get the intuition, at least you should understand. Gradient boosted decision tree is nothing complicated. You just find a gradient of the loss at every observation with respect to second argument. It may involve z. If it involves z, then plug in the previous estimate, and that's it. Okay. Once you get the GIs, so this is going to be your GIM. You get this for every observation, and then that's it. Do the regression using a regression tree. Okay, that's it in terms of procedure. Okay, so that's it. Thank you.